Hello everyone and welcome back to Network 13. Wow, it's been a while since I've released a video. But today I am doing a video on this device here. Let me zoom in so I can show you what it is. There we go. This is a DS2401 silicon serial number. And as you see, the example I have here is in a TO92 package. However, these also come in surface mount packages. So the first thing we're going to do today is look at the data sheet for the part. A little history maybe in order before we begin. The part is a DS2401. DS refers to Dallas Semiconductor, which is the company that developed this part in the first place. Dallas Semiconductor was acquired by Maxim Integrated in 2002. So you will see references in certain places to the Maxim one-wire communication interface. Now, Maxim Integrated was acquired by Analog Devices in 2021. They are currently producing these parts. So this is why we have a Dallas Semi designed part with a Maxim one-wire interface being produced by Analog Devices, and this is why we have an Analog Devices data sheet today. I hope that's not too confusing. So let's take a look here at our packages. So I bought 5 examples of this part from an eBay seller, and they're in TO92. TO92 is this radial package that you'd probably mostly associate with transistors. It also comes in a couple of surface mount packages, this XIII-223, which is 4 leads, and this TSOC, which is 6 leads. Now let's look at this pin table. So the TO92 only has 2 active pins on it, which is pins 1 and 2, which are ground and data. And as you'll see in a little bit, the data line is also used to power the DS2401. Pin number 3 is a no connect. In the XIII-223 package, they use 2 of the pins for ground, but they also still have a no connect. So two pins for ground, 1 pin for data. The TSOC has 4 no connects, 1 pin for ground, 1 pin for data, and apparently this is produced in bumped die too. Only 2 connections. Yeah, very interesting. So what does this part do? Well, what it does, when interrogated by a host controller, like a microcontroller or microprocessor, it will spit out a unique 64-bit number, and this is used for identification purposes. So, meaning if you have a piece of equipment, you want to identify it remotely somehow, or the circuit boards in that piece of equipment, or modules on those circuit boards in that piece of equipment. You can put these things on all of those parts, and as long as you can communicate with them with some kind of host controller, you can identify them with the 64-bit number. And actually you can see that here because they list applications, PCB identification, network node ID, and equipment registration. Okay, let's go over some of the other things we need to know about this part. First of all, as you can see here, we're referring to the Maxim one-wire protocol, which I mentioned earlier. The Maxim one-wire protocol on a Dallas Semi part that's being produced by Analog Devices now. This is the format of the data stream that comes out of the DS2401. It starts with an 8-bit family code, which is 01 hex for these parts, LSB to MSB, and then it streams out the 48-bit serial number, LSB to MSB, and then the last part is the 8-bit CRC value. Now the CRC is used for error detection. So the part will send the CRC value, and the host, and you'll see this later, the host will calculate the CRC value based on all of the data it's received. And if those two things match each other, then we know that we read the number without any errors. And if they don't match, the host can ask the DS2401 to resend. Now this is today's test circuit. I'm using an Arduino Uno for the host and 2 digital lines, 1 input, 1 output. The input line is connected to the data line on the DS2401, and this data line gets pulled up to 5 volts through a 2.2K resistor. Now the default state here is for the data line to be high, so this path actually powers the device when it's idle, and it only gets pulled low when we're communicating. So the host device can pull the data line low through this 2N3904 NPN transistor, pull this line low, and this is used for clocking and used for writing data, and also used when you stream data back out of the device as the clock signal. In the 2401, we have pin 1 is ground, pin 2 is data, and pin 3 is not connected. Oh, these are the commands that the host can issue. The one we're going to be concerned with today is read ROM, which is 33 hex. We'll be telling the DS2401 to stream out its number. There are other commands. There's match ROM and search ROM, but we're not going to be going over those today. Oh, here's a nice flow chart of the communications protocol between the host and the DS2401. By the way, I'm going to be posting this datasheet on the Network 13 website, which is network13.contact. And on that website, you can also find all of the exhibits, all of the drawings and the data sheets and the links and whatever else, source code, whatever else I've used to support any of the videos that I've produced. It should be in there. I can't guarantee everything's in there, but most of it should be in there. Let's say that. Okay, so very quickly, I'll go over these. The host controller initiates communication with the 2401 by a reset pulse, which is it pulls the data line low for some period of time and then releases. And then it listens for the 2401 to respond. And the 2401, if it's active and listening and understood the reset pulse, it will produce this presence pulse, which is it pulls the line low for some period of time. When the host wants to write a 1, it pulls the data line low for some low 1 period of time and then brings it high for this T slot. When it wants to write a 0, pulls the data line low for T low 0, much longer period of time, and then back high again. And when we want to stream our data out of the DS2401, the host will pull the line low for a short period of time, and this is being used as a clock pulse, and then it's going to release, and then the 2401 is either going to drive the data line high or low, depending on if it's outputting a 1 or a 0. Here we mentioned CRC generation and how this is done. Like I said, this is not a subject for this video. This is a little beyond the scope of this video today. And I think that's it. Here's your electrical characteristics table and your apps max table. That's it. Okay. Let's go on to the actual demo. So before we start the demo, I wanted to show you the Arduino program that I wrote. So we start up at the top where I declared some integer variables and also some integer arrays. Next section is the setup code, which runs only once. We defined Arduino pin 4 as an output and Arduino pin 7 as an input. We also force pin 4 low here, which is going to default the data line high. We start the stream to the serial monitor here, 9600 baud, and then we wait 500 milliseconds. Then we start the main loop. So we increment loop counter and we go into this do while loop here. If there's serial data available, we are going to read the character that's there, put it into incoming byte, and if incoming byte is a lowercase r, then we're going to print the loop count and a tab character, and then we're going to break out of this loop and execute the rest of the code here. So next we will pull the data line low. This is the reset pulse for the 2401. We're going to wait 500 microseconds, and then we're going to release the data line. So if the DS2401 acknowledges this and everything's working properly, it should pull the data line low, and this is what we call the presence pulse. Now, we're not looking to detect that in this particular program. We're assuming that that's just going to work, so we're skipping that. Next, there's a 1 millisecond delay, and then we issue the read ROM command to the DS2401. Now let me jump down to that function. Now read ROM is writing hex 33 to the DS2401, writing this least significant bit first. We're going to send a 1, a 0, a 0, that's 3, and then a 1, a 0, 0, that's another 3. And the commands here, the functions here rather, write 1 is pull the data line low for 5 microseconds, then release the data line, wait 120 microseconds. That's to write a 1. To write a 0, pull the data line low, keep the data line low for 100 microseconds, and then release the data line. So let's go back up to, here we were. Now once read ROM command has been sent, we can start clocking out the actual serial number, the 64-bit number that's in the 2401. So we start with the clock edge. We pull the data line low for 10 microseconds, and then we release the data line. We wait another 10 microseconds. Then we read the state of digital pin 7. If digital pin 7 is high, we write a 1 to the corresponding element in the array, and if it's a low, we write a 0. And then we wait 100 microseconds, and we do this 64 times. It's going to be 1 for every bit that we're streaming out of the 2401. And we're storing them in order in the read data array. Read data array is, of course, 64 elements. After this, we have to process this data. So what I'm doing here, and this is allowing me to, a couple of things. It's allowing me to represent the data as hex numbers or hex characters. So I take 4 bits at a time, starting at element 63, and I calculate what this value would be, and then I print it to the serial monitor as a hex character. I take the next 4 bits, calculate this into another hex value, send that to the serial monitor. Now, these are 2 special cases. If we're starting at element 63, this is going to be the CRC value is going to start here. So we go 16 times the high byte plus the low byte. That would be the CRC value. And if we're starting at 7, that's going to be the family code. So we go 16 times the high byte plus the low byte. So these are special cases. And then we print the CRC value, the family code, and down here we are going to calculate the CRC value from the data that we have, that we've recorded. So what I'm doing here is I'm modeling a piece of hardware, which is an 8-bit shift register, and it's kind of tough to explain exactly what this is doing. This could be a whole video in itself, but it's an 8-bit shift register, and it's got a couple of exclusive OR gates that are used to generate the CRC value. So this is the software version of that hardware. I end up calculating the CRC value, all these different bit weights, I add them together, and I send that to the serial monitor, calculated CRC, that value. And then I do a compare here. If the calculated CRC value equals what I read from the DS2401, I say, oh, it's a match, and if it doesn't, I say it's a mismatch. And that's the end of our loop. And then we wait 500 milliseconds, and we go back up to the top of the loop, and we wait for the next character from the serial monitor. And if this is not an R, we will be in this do-while loop. If it is an R, then we will break out of this and we'll do this all over again. So that's the software. I will be posting this source code to the Network 13 website. Now, let's upload this to the Arduino, and we'll go over to the serial monitor and we'll issue a read command. So the device I have in the board right now, this is the family code. This is the 48-bit serial number here, and this is the CRC value. So I print this out to the screen. CRC is 23, family code is 1, it's actually 01. I say the calculated CRC is also 23, and we have a match. Now, if I do this over and over and over, it will give us the same data. Now, if I introduce an error right now by pulling the DS2401 out of the breadboard and we try to do a read now, it's going to read a bunch of nonsense. It's going to read all highs, all ones. It's going to say the CRC is FF here. The family code is FF, which is here. The calculated CRC, it's telling me, is 0C, and it says, oh, FF doesn't match 0C, so we have a mismatch, which means that the error detection is working. I plugged in another 2401, a different part. Let's read that one and see what we get. Okay, so it's got a different serial number here. It has a family code of 01 because the family code is the same for all of the 2401 parts. It has a different serial number than the other part, and it has a different CRC than the other part, which it should. CRC that we read is E5, family code is 01. We calculate the CRC of E5, so we have a match. So that's a good read. I'm going to try the third 2401 that I have that works. And let's issue a read command. And you see this one's different as well. This has a family code of 01. It has this serial number, which is different than the other two serial numbers that we read, and the CRC value is EA. So CRC, EA, family code 01. My calculated CRC is also EA, which means I have a match, which means I have a good read. So now we're going to go to the bench and we're going to look at these signals on the oscilloscope. We're back at the workbench now, and I wanted to show you the test circuit wired up here on the breadboard, but there really isn't much to look at. I mean, here's the Arduino Uno, obviously, over here on the breadboard, and I'll zoom in on this. We have the DS2401 is here. Inside here you can see a 2.2K pull-up resistor. Over here is the 5K resistor going to the base of the 2N3904, and then buried inside there someplace is the 2N3904. I think you can see it there in the center, and of course everything else is just a bunch of jumpers. I did put a electrolytic cap between the 5-volt rail and ground just to clean things up a bit, but the far more interesting part of this will be on the oscilloscope screen, and we'll get to that in a moment. So this is idle state right now. If I force the trigger, you'll see that the data line, which is the yellow trace here, the data line is at 5 volts. I have the trigger level set for 2.5 volts there. Now let me send a read command, and we're going to be looking at right now, this is going to be the reset pulse and the presence pulse. Okay, so this here is the reset pulse, which goes low for 500 microseconds, and then the DS2401 takes over and pulls the data line low, and this is our presence pulse here. Alright, I've got this set up for the next shot now. I'm going to send a read command, and what we see starting on the left is we see the very end of the reset pulse, and that's the presence pulse, and then we have a delay here. And then we start sending the read command to the DS2401. So we have 11001100, which is 33 hex, which is the read rob command. Now let's see if we can take another shot here. Now we start to see, after the read command, we see the 2401 streaming data back to the host, and it looks like it's going to be 10000000, which is the family code, which is 01 in hex. So let's roll this over a little more, and we'll say we're going to start there. Now, according to my readout on the serial monitor, the next number should be 00. So that's not very interesting either. That's all of this. So I'm trying to get this to a point where it actually looks like different bits being sent. Here we go. So here we see highs being sent, we see some lows being sent. You can see the difference here. And this just goes on for 64 bits as we scroll. Highs and lows, highs and lows, highs and lows. It's a little difficult to make sense of like this, but the Arduino host controller isn't really having any problem with it. It's reading it really well, getting CRC matches. And here we get to the end. So this would be the most significant bit getting streamed, and then we go back to idle state after that, which is data line high. Okay, this concludes the video on the DS2401 silicon serial number. If you have any comments or suggestions, please feel free to leave them in the comment section below the video, or you can write to me at network13.contact@gmail.com. That's network13.contact@gmail.com. If you enjoyed the video, please consider giving it a thumbs up. And if you enjoy our channel and our content, please consider subscribing. We are at 994 subscribers as of today, which is September 18th, 2022. And I thank each and every one of you who's bothered to subscribe and who's been following the channel these few years and who's been enjoying the content and giving me constructive and encouraging feedback. I really appreciate it. And with that, I will say, as always, thank you for watching.